Well, thank you very much for the invitation. Sam, happy birthday. I want to say one of the joys of doing mathematics is having colleagues like you as a co-author. So congratulations. So I'm going to be talking about the structure of the polyhedral product functor. Fred did a lot in his first talk. And so he also gave the history and all the credits, and I'm going to refer to Fred's lecture for that. Some of the people who did the foundational work in the subject are in this audience. So the polyhedral product functor and the related spaces, the story starts with the structure of toric varieties, which are given in terms of combinatorial data, which the buzzwords are something like the simplicial fan. Oh, the baby, this is this guy. It hasn't changed. It looks the same. In fact, that smile, I think I was told that was shortly after he found his first non-trivial non-immersion of a real projective space. So I don't know how old you are at this point, Sam, but they shaved it for the picture. So, sorry about that. So in any case, the talk is going to be about the foundational work of Davis and Januszkiewicz. They gave an algebraic way of dealing with smooth toric varieties. What they did is they constructed something called the moment-angle complex, which is a manifold, and found a free action of a torus on this manifold, modded out by that action, and in that family of manifolds that were generated, all the smooth toric varieties appeared, as well as other manifolds. So this family is called quasi-toric. They include those that were known through algebraic geometers. The work this was eventually generalized. The moment-angle complex was generalized, cleverly called the generalized moment-angle complex. The name was eventually changed to the polyhedral product functor. And Sam, Tony, and Fred have been thinking about the topology of this guy for a number of years, and my talk will be to describe some of the results we've obtained in the structure of the polyhedral product functor. Let's see. Oh, one of the few things, I mentioned most of the references, et cetera, were done in Fred, but as far as I know, the first appearance of the polyhedral product functor appeared in the thesis of Porter. I first read about it in Strickland's work, and it was Bill Browder who rechristened this guy the polyhedral product functor. So let me briefly recall what Fred did to give the definition of the polyhedral product functor. The story begins with K, a simplicial complex on M vertices, and associated to each of the vertices, I have a pair of spaces, pair of CW complexes, Xi, Ai, and it will eventually have to insist that Ai have a base point, a point, no pun intended, that Fred made a big deal about. We'll call the collection X underline A underline, and we're going to construct a space associated to every simplex in K. And I'm using X up a sigma, Fred used D of sigma, and it's a product of yi's. The yi is xi if I belongs to the simplex, and ai if I does not belong to the simplex. And we think of x sigma as living in the product. Now, I want to make a point. This type of construction, where you have either a space or a group associated to the points in the simplex, and another set of spaces or groups for all the points not in the simplex, will permeate the lecture. That'll occur 3 or 4 times, a variation of that. So just keep that in mind. So given this data, we take the union, and the union is taking place in the product x1 through xm of all these x sigmas, and we call this the polyhedral product functor, and the variables are indicated in the notation. For later in the talk, it's useful to think of this in the following way. There's a category which the simplices of K and the morphisms are given by inclusions, and then that produces a diagram of CW complexes where the image of sigma is this X upper sigma, and this polyhedral product functor is a colimit of this diagram. And I want to point out that it's also, because of the nature of the maps involved, it's also a homotopy type of the homotopy colimit, which will be important later on. Why? Because all of the maps included in the diagram are closed cofibrations, and there's a theorem that if you have a diagram of everything are closed cofibrations, the homotopy colimit and the colimit are the same homotopy type. And that's exactly what's happening here. Okay, so we have this polyhedral product functor, and then we have these spaces constructed by Davis and Januszkiewicz. And what do they have to do with each other? Fred gave away the punchline. But Davis and Januszkiewicz restrict their attention to polytopes, a simple polytope, which I'm not going to describe what simple is, but it's a reasonable condition on a polytope. So starting with a polytope, you can construct its dual, K sub P. This is a simplicial complex. I described how you associate to each codimension L face in P an L-1 simplex in Kp, and there's a very precise way of constructing the duality. And the theorem is that the polyhedral product functor for the dual simplicial complex, D2S1, is the moment angle complex that Davis and Januszkiewicz constructed for P. Right. 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 The variations on the English are correct, but I want to use those terms just for simplicity, but you're quite right, of course. I mentioned that Fred's comments and all the references were made then. I just don't want to repeat them all, but the foundational work was done by people in the audience. Now I'll point them out. Okay. By the way, this moment angle complex, or whatever you wish to call it, is a manifold. That's going to be important later. Its dimension is n. The polytope started life as an n-dimensional polytope, plus the number of vertices in Kp. That's equal to the number of facets in K, i.e. the codimension 1 faces. So there is a number here, which is the dimension. And it has a natural smooth structure, indeed. So they don't, but I think, well, let me go into, we later on deal with the smooth structures, but I don't want to deal with those right now. Now there's an action of the torus, the M torus. M is the number of vertices on the moment, I'll call it the polyhedral product functor D2S1, which is coming from the obvious action. And whenever you have an action of a group on a space, it's impossible to resist forming the the Borel construction. So there's the Borel construction using the torus, and I guess it depends on the model one uses the ETM. That's not important for what I'm talking about. And this space is called the Davis-Januszkiewicz space. And the cohomology of the Davis-Januszkiewicz space, as Fred mentioned, is this important combinatorial invariant called the face ring. Remember, this whole story started with the toric varieties, which came from a combinatorics. Here it's being resurrected in the context of this theorem. And I'll briefly review what the what the face ring looks like, because we'll be coming to generalize it later. You take a polynomial algebra on two-dimensional classes, one for each vertex. You look at the ideal generated by square-free monomials where the subscripts do not span a simplex. And that gives me a combinatorial invariant of the simplicial complex. This gadget, the Davis-Januszkiewicz space, is also an example of a polyhedral product functor proved over here. And it's the one where we take CP infinity comma a point. Now, when I don't have the underline, as Fred used the notation, that means over every point I put the same space, CP infinity comma a point. Now, I'd like to review the stable splitting, which gives a canonical way of splitting well, one suspension is all that is needed to split the polyhedral product functor for any space, any pairs XA. So we need some information to be able to do this. Well, the first, and I think Fred covered this in his lecture as well, and I apologize for referring to earlier lectures, I shouldn't do that. We can make a functor analogous to the polyhedral product functor called z hat. Well, all we do is replace the product that occurred in all those definitions with the smash product. And it's here that we need the base point. It's crucial for this construction. So, for example, these x sigmas that I defined back in the polyhedral product functor, if you push them down into the smash product, you end up with the smash product of the y's that replaced the x sigmas, and these are defined in exactly, the yi's are defined in exactly the same way as they were defined for the polyhedral product functor. Next bit of data. For a set of numbers between 1 and m, I can form something called the full subcomplex k sub I, which is contained in k. And that simply is you look at all the vertices in k, all the simplices in k whose vertices lie in I. That gives me a subcomplex. That's called k sub I, the full subcomplex. And the theorem is that the suspension, one suspension of the polyhedral product functor breaks up as a suspension of wedges over all subsets of M, including the empty set, of these z hats for all the full subcomplexes. Now, without more information, we've taken the suspension of something we don't understand and wrote it as a suspension of a lot more pieces we don't understand. However, sometimes we can say something about the z hat. So when the xi's are contractible, remember the xi's are the first variable in the pair. When the xi's are all contractible, we can actually describe z hat completely. This is called the wedge lemma. The z hat for k xa, that's what the underlines, so the spaces are varying, is the geometric realization of k join the smash product of all the a sub i's, one for each of the vertices. And that actually is a very useful, that gives us a lot of information about the cohomology of the moment-angle complex. I'd like to specialize to x equal to one disk, this actually came up in earlier lectures, d1 and a as a zero sphere. That's a special case of this. Well, in that case, this a hat is just a zero sphere. And then the join is just a suspension of the geometric realization of k. So now let's feed that back into the splitting theorem. If I wish to take a look at the suspension of k d1 s naught, now I'm going to call that the real moment-angle complex in the sense that the d2s1 case was the complex moment-angle complex. We find that it has decomposed as a wedge of these spaces, which are simply, essentially, the geometric realization of all the full subcomplexes. So what I want to do with this, and I'm going to use words which perhaps I can't define, but I'm going to use these words later, is that the cohomology of this real moment-angle complex induces a pairing on the cohomology of the subcomplexes using this decomposition. And this pairing was described in a paper which Sam and Fred and Tony, and I'm going to use the phrase, the pairing on the subcomplexes induced by the cohomology of the real moment-angle complex later in the lecture. So hopefully that will not be completely forgotten by the time I get to it. Okay, here's a quick example to illustrate what I've been doing. Take a square with 4 vertices. Then we're only interested from the wedge lemma in the k sub I which are not contractible. Well, there are only 3. There's 1 and 3, which is a 0 sphere, 4 and 2, which is a 0 sphere, and the whole guy, which is a 1 sphere. Feed that into the decomposition using the wedge lemma. We're going to get a 0 sphere join. Now I have 2 copies of the circle, one for each vertex. That gives me the 3 sphere. Similarly, I get a 3 sphere for 2, 4. And if I use the entire 1, 2, 3, 4, well, the geometric realization is a circle. I now have 4 copies of the sphere, of the circle. That's giving me the 6th sphere. So at the end of the day, the decomposition plus the wedge lemma give me a wedge of S3 with S3 with S6. Now Z, the moment-angle complex For the boundary of a square, D2S1, I had mentioned was a manifold. If you put in the numbers, it's a 6 manifold. It's S3 cross S3, and the stable decomposition is the usual decomposition of that product in terms of that wedge. Okay, now I'm going to start going into some work that we've done beyond the definition and the splitting theorem. Now, what I'm going to do, this is actually a little deceptive. Only at the very end am I going to bring in polytopes and manifolds. For what I want to do, I am going to simply restrict myself to constructions on a simplicial complex. And these constructions are motivated, I'll try to motivate them, from the splitting theorem and the wedge lemma. We can form the polyhedral product functors using different spheres at each vertex. D2S1 gave us the moment angle complex. These guys, when you're using different spheres, look like they're genetically different. Now, I actually like Soren's idea of introducing animals into a lecture. So I'd like to call the moment angle complex, D2S1, a wolf. And these guys I'm going to call sheep. And that actually is a hint as to where this theorem is going. But we'll see what that happens later. The wedge lemma suggests some family resemblance between these two guys. Let's consider k equals 2 points. Over one vertex, I put D2S1. Over the other vertex, I put an exotic situation, D4S3. Then I use the wedge lemma. I'm only using the z hat parts. I really want to make a statement about z, but I'm talking about z hat. And I get this 5-sphere from the wedge lemma. Now, we'd like to get rid of the 3-sphere and replace it with a 1-sphere, which is what the moment angle complex is built out of. And we could do that, as it turns out in this example will illustrate it, by replacing the simplex with something bigger. So in this example, if I happen to take z hat of the boundary of a 2-sphere, now there are 3 vertices, but I do the D2S1, the wolf, I get the 5-sphere again. And this process of playing off the spheres against a simplicial complex is part of a very general construction, which I'd like to describe. Well, first I have to sort of give you a little bit of a way of thinking of a simplicial complex. It is completely determined by what are called its minimal non-simplices, and I'll have an example later on. A minimal non-simplex is a subset of M, which is not a simplex in K, but every further subset is a simplex. And these completely determine the simplicial complex. So to continue the metaphor, I like to think of this as the DNA of the simplicial complex. So given a simplicial complex K with vertices V1 through Vm, and integers J, J1 through Jm, one for each vertex, I'm going to make a new simplicial complex by altering the set of vertices in the original simplicial complex. Namely, we're going to replace the set of M vertices with a set of sigma Ji vertices, and I'm calling this a set change operation on K. So what we do is form a new set where each V is now a set of vertices. V sub I is now replaced with J sub I vertices. So that gives me the set of vertices. Now I've got to give you the DNA, which is to say the minimal non-faces. Well, all you do is capitalize the minimal non-faces, which have the little v's. You capitalize the v's to form the minimal non-faces in the new complex. Specifically, all of the minimal non-faces are given by such a set of vertices if and only if, same subscripts, this was a minimal non-face in the original simplicial complex. So I decided here's an example. The minimal non-face is V1, V2, so I'm looking at the cone on 2 points. I'm going to double the V2, so it's replaced by 2 vertices. The minimal non-face has to be V1 and these 2 guys, in the sense that at least these have to be a non-simplex, and no subset can be a non-simplex. Every subset has to be a simplex. I might be screwing that up, but essentially it says the minimal non-face has to be that boundary of a 2-sphere. So K121 is the cone on a boundary of a triangle. So that's an example of the construction. And here's the theorem. The Z for this is the sheep, Z for the mixed spheres over each coordinate, is in fact a moment angle complex for Kj. So the phrase I like to say is, this is really a wolf in sheep's clothing. That was, well, sorry about that. So in fact, these things are in fact just examples of moment angle complex. Fact, if K is dual to a simple polytope, then so is Kj. Remember I mentioned that in Davis and Januszkiewicz's original constructions, if they have a simple polytope, they form the moment angle complex and have tori acting, yes? They have tori acting freely on the moment angle complex, and the quotients give quasi-toric manifolds. The J is a set of integers, one for each vertex. So D upper 2J would be above, let's say, the first vertex would be a 2J1 disk modulo its boundary. The J's are simple, are sequence. Well, what I'm doing is, okay, I start with M vertices. So let's take a look at the first vertex, V1. I replaced V1 with V1J, well, that should be V11 up to V, that's a typo. That should be V11 all the way up to V1J1. So I replaced V1 with J1 vertices. I take a look at V, and I call that capital V1. It's a set of vertices. I replace V2 with V2 new vertices, and I call that V2. That collection is a new collection of vertices, and I describe the minimal none faces, and that determines a simplicial complex. That's the sequence of ideas. So, oh yeah, so we get an action on each one of these guys, producing a manifold. So what happens, I start with the dual of a polytope. I go through this construction. I get infinitely many moment angle complexes. I do Davis and Januszkiewicz's action of the torus, and I get infinite families of manifolds associated to a single polytope. So for example, if I start with just 2 points and go through this process, you can construct all the complex projective spaces. Yes? Excuse me? I know I didn't want to get into the, yes, there's an analogy. If I didn't want to use even dimensions, I could use that, but I wanted to stay within the world of the complex. So that's an example. That shows how one modifies these constructions to get infinite families. Now I'd like to get into the cohomology of these moment angle complexes. And here are the steps. We're first going to construct a spectral sequence converging to the cohomology of ZKXA. Then we're going to assume some rather strong freeness conditions to compute the differentials. Then having a formula for the differentials and a bit of bookkeeping, we'll be able to compute the E infinity term. And I didn't say it here, but there are no extensions, so we actually will have the cohomology of the moment angle complex. And we'll be able to say something about the ring structure, but in order to simplify things, I'm actually not going to say much about the ring structure in this lecture. So I'm going to describe the spectral sequence for the Z hats. Remember, the Z hats are the building blocks for Z, and it's a little bit easier to describe the spectral sequence for Z hat. First of all, the vertices of K are ordered. They came from the numbers from 1 to M. That implies an ordering on the simplices by using the left lexicographical ordering on the vertices that occur in a simplex. And if there are different dimensions, the bigger dimension is bigger than the smaller dimension. And now the spectral sequence, you do the most obvious thing you can think of. You add one vertex, one simplex at a time to K. Let's call the resulting filtration Fs of Z hat. What that means again is I take a look at Z hat and replace K by the result of adding the first S simplices using this lexicographical ordering. And the E1 page is the usual, the cohomology of the relative groups. So the question becomes, how can we identify the cohomology of these relative groups? Here's the answer. Again, remember I mentioned we're going to see this pattern of certain spaces occur for vertices in a simplex and certain spaces occur for vertices not in a simplex. Well, here it is again. For every simplex in K, and I'm adding over all the simplices, I take a copy of the quotient x mod A for the vertices, and I take a copy of A for the non-vertices. That gives me a group that's at least E1. To get the spectral sequence for Z, you just add these up for all the for all the full subcomplexes. And I will actually describe the resulting E1 term. It's a little bit more complicated, but I'm going to describe the resulting E1 term in an example. So Fred mentioned the result of Coxeter about what happens if I take D1 S naught and put for K a polygon, an n-gon. And he mentioned that you get a surface. You always get a manifold. It's an orientable manifold. It's a surface. And the question, what is the genus of this surface? What I'd like to illustrate, and there are many easy proofs of it, I'd like to illustrate how the spectral sequence gives an easy answer to this problem. And this is to illustrate how this is my attempt to give an illustration of how the spectral sequence works. So we're going to compute the Euler characteristic of the E1 page, which of course is the Euler characteristic at the end of the story. And all we have to know is that the boundary of an n-gon has n0 simplices and n1 simplices. So here we go. I'm afraid that I have to tell you what happens when you assemble all the E1 terms for the Z hats. You get essentially the same thing, except before, if you recall, I had the smash product of the A's over the complementary vertices. What this means is I take the product of the A's. I should have written it out like that. And the smash product between the two pieces. Here's a piece indexed by the simplices. This is the piece indexed by the complement. You take a right half smash. Don't worry about the details. It can be easily deduced from the result I gave for the spectral sequence with Z hat. So we're going to compute the ranks of these guys. So here we go. First, you start with the zero simplex. Whoops. There we go. There's nothing here. The zero simplex, there are none of these factors. So all I have is a product of zero spheres, one for each of the vertices. So I have n of those. There are n vertices, recall. You figure it out, and you have 2 to the n zero-dimensional classes being contributed from the empty simplex. When you go to the zero simplex, you have one. Each of these pieces for every simplex gives 2 to the n minus 1 contributions to the Euler characteristic. But there are n zero simplices, so at the end of the day, you end up with n times 2 to the n minus 1 one-dimensional classes. And I'll admit it's not the best way to present. It's actually an easy calculation, but maybe it's not obvious from that. That's the right half smash. Right. So let me show you what the half smash is. The half smash is the smash product where I put a disjoint point on the right factor. I think I wrote it out here. Okay. So you get a bunch of copies of two-dimensional classes, and you multiply it by the number of one faces, and you find that you have a total of n times 2 to the n minus 2. 2 cells contribute to the Euler characteristic. Add it all up. Oops, that's not adding it all up, this is. And you get an Euler characteristic from the E1 term of the spectral sequence. Well, the Euler characteristic determines the genus, and there it is. That's exactly Coxeter's theorem. Actually, you can prove a very general result if K has T to the n simplices, and the Euler characteristic of the moment-angle complex is given by this formula. And you just have to consider the empty simplex to be a minus 1 simplex. So you get an answer in general for arbitrary situations. But on the polygon, the polytope, which is what we start with an n-gon. On the n-gon, we took Z of K of a polygon D1 S naught, and the K is a polygon, so it has n vertices and n edges, and n one simplices. And from that, you have to get a surface and I'm trying to deduce what the Euler characteristic of that surface is, and hence what the genus is. From the, yeah. Okay, all right. Now the differentials in this spectral sequence, this depends on a very strong freeness condition, which is written here. We have to assume that the cohomology of the AKs decompose as a sum of two free groups. The cohomology of XK decomposes as a sum of free groups. And the long exact sequence is particularly nice. Well, it's indicated by the labeling. The B goes to the B by the map in the long exact sequence. The EK would be the co-kernel of the map, and the CK would be the kernel. Specifically, I try to write it out here. This is what I just described. These are how these groups match up. So it's important. I'm going to make this comment a number of times. The C's and the B's come from the cohomology of X. That'll be useful to us. That's something I could remember. So we're going to have to use this E, B, and C to describe the E infinity term of the spectral sequence. To do that, I'm afraid I need some more notation. And as I said, we're not going to describe the ring structure completely because I'm getting tired of putting in all this notation. So we're going to be finding a sum of groups, and they're going to be indexed by subsets of M. So for each subset of M, I'm going to be looking at simplices that have vertices in I and are simplices in K. So I'm only restricting myself to I now. Now I'm going to find a group, which I'm denoting Y upper I sigma, and it's a product, a tensor product of groups, P many, one for each of these entries in I. And what it is, you take a C, remember C are one of these subgroups, if the IT belongs to sigma, and B if it does not. So here's another example of this phenomena. You put some junk on the vertices that are in sigma, and some other junk on the vertices that are not. Next thing we need, again, I is still this subset of M, and sigma is a simplex in I that's a simplex in K. And this will denote the link of sigma in the complement of I. What that simply means is that I'm going to look at a simplex will be in Ni sigma, I call it sigma bar, if all the vertices are in the complement of I, and sigma bar union sigma belongs to K. So again, I'll give an example later on, I just want to get the notation down. And here's what the cohomology as a group looks like, given this strong condition, freeness condition on the spaces. So this part here, it's summed over all the i's in sigma. This part here, it just involves pieces that come from the cohomology of X. Remember, the Y was built out of C and D. It'll be important for the example to remember that X lives here. The E lives in A. It was this co-kernel part. And this is the cohomology of the suspension of the geometric realization of the link. That's the group. And as an example, I'll show one could take from the formula I gave here. I'm going to extract the Poincare series for the moment angle complex. And all I did was replace the entries that are in this decomposition and put the reduced Poincare series and a parameter T. It just is what's necessary to make all the dimensions work. So this formula just extracts some information from the formula I wrote. So here's an example. And I'm not going to go through the whole thing, and it's tedious, but at least I'll show you how the things may be working. So I'm going to look at the simple simplicial complex. It has 3 vertices and 2 edges indicated here. And I'm going to pick a space X, which has a group B in degree 4 and C in degree 6. What that means is, remember that the cohomology of X decomposed as to the B part and the C part. So there's one guy in the B part in degree 4 and another guy in the degree part in degree 6. And the cohomology of A, I'll put in a 2-dimensional class in the co-kernel, and the B matches to the B. These examples come from truncated projective spaces. I just wanted to give a non-trivial example. So let's take a look at how the calculation starts. I could be the empty set. That's how it could start. So the only simplex is the empty set. Going back to the example, the n, well, the n, remember, was the link, this time the link of the empty set in the complement. That's my entire K. That's contract. These results were obtained by different methods by Q Zhang. Next, I'd like to, there's another spectral sequence about. a homotopy co-limited spectral sequence. So remember some time ago, I made some noise about the fact that the co-limit, in the case of the moment angle complex, is of the homotopy type of the homotopy co-limit. And what I'd like to do is redirect the focus from the moment angle complex, for an example, away from the spaces and to maps. I want to use this machinery to construct invariants of maps. And I'm going to use, as an example, I'll show how the total bracket comes out of this machinery. So we start again. K is a simplicial complex on M vertices like we've had all along. But now, instead of over each vertex I'm putting a pair, I'm going to put a map, F sub I. For point set topological reasons, I'm going to take that to be a CW map. I'm not sure if you actually need that, but let's assume that. The example we had before the map was an inclusion, but I'm no longer assuming this is an inclusion. And I like to think of this, there's the source of the map and the target of the map, because one could do this in a very categorical setting, and that would be the words we'd have to use. Now I'm going to define what I might call the polyhedral mapping functor. And it starts in the very similar to the way we did the polyhedral product functor. For each sigma in K, I'm going to take a product of the y's, where I take the target of the map if J belongs to sigma, and the source of the map if J is not in sigma. Again, a pattern we've seen a number of times. Now this gives us a diagram. Namely, a diagram that is induced exactly as it was before by the inclusion of the simplices. But now, when I want to define the map from X sigma to Xj, I don't have inclusions, but over the relevant factors, I use the map Fi. That's where the map Fi rears its ugly head in this construction. And the polyhedral mapping functor, well, what else? It's going to be the homotopy co-limit of this diagram. That's all that it is. It's a homotopy invariant. So I want to point out after homotopy, I haven't done anything new, because I could simply replace all the maps by inclusions up to homotopy, and I will get the usual homotopy polyhedral product functor. But for the examples I wish to do, as I say, I want to focus on maps, not spaces. This seems to be a more convenient language. So I'm going to give an example where K is two distinct points. Here are the ingredients. We begin with the map F1 from the n-1 sphere to Sm, and a map F2 from the M sphere to FSR, and I'll assume the composite is homotopically trivial. Now I'm going to let the space Y be the mapping cone of F1, and because of the homotopy triviality condition, we get a map from Y to the R sphere. Just extend the map. Now this map, it's not unique. It depends on the choice of homotopy. But I made some comments that there's a total bracket here. The indeterminacy is starting to rear its head right now. There's also a map, just collapse to the top cell. So I'm going to form the polyhedral mapping functor. K is 2 points. Over one point I put omega. Over the other point I put nu, the two maps I just described. Well, ignore the word reduced. The whole homotopy co-limit spectral sequence is very simple in this case. It has one group infiltrate, well, there's essentially one group infiltrate. Oh, I forgot to say, I'm not computing the homology, I'm going to apply the stable homotopy functor. I'm actually trying to compute something about the stable homotopy of this zk omega nu. I want to look at that particular functor. I forgot to say, everything I did before can be applied in a generalized cohomology theory. In this case, a homology theory. I'm using stable homotopy for this example. So there's one, oops, what happened? There's one group in filtration 1, and we have the two groups in filtration 0. Now, I'm going to look at the D1. I'm really interested in the first differential in the homotopy co-limit spectral sequence. But I'm actually just going to look at D1 on classes which are in the image of the diagonal maps. I'm restricting my attention to some classes. And I'm not even going to look at the complete targets. I'm going to project out onto the two spheres. So this composite gamma is basically a part of D1. And here's the result. if beta plus alpha is in the image, so it's the sum of two groups, if beta plus alpha is in the image of this map, then first of all, the alpha has to compose trivially with F1, and beta is the total bracket. There's a sign, and I think I've got the sign right, I'm not 100% sure, but beta turns out to be the total bracket of F1, F2, F1, and alpha, modulo indeterminacy. And the proof uses a description of the total bracket due to Brooks-Shipley. And using generalizations of Shipley's work, you can actually show that the n-fold total bracket appears in the differentials of a suitable homotopy colimit spectral sequence. What other invariants of maps are stuck in the spectral sequence, I don't know, but I thought the total bracket would be a good example. So we have seen that the polyhedral product functor is a uniform setting for constructing interesting families of manifolds, studying problems in combinatorics, geometry, toric geometry, and I like to think some classic homotopy, stable homotopy theory. And I have to say it's been very exciting working with Sam. Thank you for that, and happy birthday. I think I ended early.
For some questions? No questions?
Oh.
There's questions.
Well, in some sense, it helps compute the differential because if that total bracket is non-zero modulo indeterminacy, it means that differential has to be non-zero. But it's not clear that it gives me the complete calculation of the differential. It just gives an existence of perhaps a non-zero element, a non-zero differential. It would force a non-zero differential. I was simply looking at it. I'd like to see constructions I know from my youth from homotopy theory appearing in this machinery, but actually to use it to compute the homotopy colimit spectral sequence, I'll use the phrase work in progress.
Yes.
Functorial. I wonder if your functorial viewpoint of these polyhedral products can be used to interpret your homology calculations or cohomology calculations. So you started with a functor from the poset determined by the simplicial complex to the pairs of CW complexes?
Correct. Pointed pairs, to be precise.
Yes. Now you could have another functor to graded abelian groups given by the homology of that pair.
Right.
And so there's an obvious natural transformation between them. So can the theorem be interpreted as saying that how do I want to say it? That when you pass to homotopy colimits of these two functors, the natural transformation gives you
an isomorphism.
An isomorphism in homology.
Actually, I'm not sure if there's some more detail as to one put in. In fact, remember these functors are constructed from products and smash products. So one could make a very categorical definition and say, suppose I have some kind of a reasonable, even an operand or something, and I could do it in an algebraic setting and get the maps you describe. And the spectral sequences don't seem to give the isomorphisms you suggested. I think with some more hypotheses, the answer is yes. But one has to really look carefully at, for example, if one wants to get the ring structure, so carrying your argument to the ring structure, you have to look very carefully in the details of how this is done, and that doesn't seem to be carried by such a construction. But you might be able to get the group structure. I just really am not sure if there's just how it works, because the details are a little difficult.
Okay, well, maybe we should continue that over coffee, because otherwise we won't have any time to drink.
Well, you mean the composite functor spectral sequence is what you mean? Or the homotopy colimit spectral sequence? Yeah.
Okay.
Well, the homotopy colimit spectral sequence is the Balanced-Field-Kahn. What you're saying might be a version of a composite functor spectral sequence where one of the functors is the homology. So I really don't know. I haven't thought about it from that point of view. There are other points of view which have not worked that might be a better point of view.
Okay, well, let's thank the speaker one more time. And we have a coffee break, I guess, so we meet again here around 12, maybe 12:05. Coffee is somewhere. No, sir.